right. Hello, everyone. My name is Marius, and I'm going to talk about Go Ethereum today. I didn't have much time to prepare my slides, as you can probably see on the side. I'm just going to wing it, and we're going to go a bit into the code. I'm going to talk a bit about what the different modules of Go Ethereum do. And then I thought we had we can just make a lot of time for questions and discussion and stuff like that. All right, I wanted to show you how a transaction travels throughout Go Ethereum. And this is the rough overview. We submit a transaction via RPC, and it gets inserted into the transaction pool. And from there, we have the ETH package, which handles a lot of So we have the ETH protocol, which defines the network messages and stuff like this, and the way we interact with the network. And from there, we take the transactions, and we send. We use the peer package. We're going into the peer package and send the transaction to another peer. This peer goes the same way back through the ETH package into the transaction pool. All right. I think it's most interesting to actually see it. So when you send a transaction via MetaMask to your local node, then you will always send a raw transaction. You will sign the transaction not in your node, but you will send the signed transaction to Go Ethereum, and it will end up here. And from there so this is internal ETH API has a lot of these API methods that you're very familiar with, like ETH send transaction, ETH send raw transaction, ETH get block. All of these are defined in internal ETH API. And if we follow this, now we submit the transaction, and what we do some basic checks before inserting it into the transaction pool, and so we check that we have enough fees, and that the fees don't exceed a certain amount, because we had a lot of people mixing up the value of the fee and the gas price, and so they were sending transactions with a really high gas price, and then they were complaining, why did I lose so much money? And so we have some extra checks there to make sure that this doesn't happen. And then we go to send transaction. Send transaction is actually in the interface from the transaction pool. So this is implemented by the transaction pool, this interface. And we end up send transaction, send TX, something like this. No, not here. Oh, we end up in the API backend, sorry. Send transaction is in the API backend. The API backend is something that we use for a lot of these APIs, and it's a collection of methods that are useful to have for creating the RPC APIs on top of that. And one of them is send transaction. Send transaction just adds the transaction as a local transaction into the transaction pool. So if we follow this, we come to the transaction pool, add locals, add transactions. So the transaction pool, it has all of the transactions, of course, and we sort them. We sort them by the gas price, and we also have with 1559, we have a two-dimensional gas price. Sorry? Oh, okay. A two-dimensional gas price, and that is it's a bit more complicated how to sort the transactions because some of the transactions might be valid at a certain base fee. Some of the transactions are not valid at a certain base fee, so we have to continuously update which are the valid transactions because we built a pending block. The pending block is just the current block that you have, and you pile all of the transactions on top so that you know roughly how the next block will look like. With the emergence of a lot of this MEV stuff, this pending block is basically useless, and we're trying to get rid of it. The problem is that the pending block is used everywhere, and for example, if you create a transaction, you will need the nonce, right? And if you already send a transaction to the transaction pool that is not confirmed yet, you will need to know that there's some transaction, so you can increase the nonce once more in order not to replace the transaction. If you send the same transaction, you actually replace it. If you send a different transaction with the same nonce, you actually replace the transaction, but only if certain conditions are met, and the conditions are the max base fee per gas has to be 10% more than from the transaction that you want to replace, and the max tip per gas also has to be 10% more. And there's some discussion about this, if this is actually the right mechanism. But the problem is if we don't let, if we don't have this, if we let someone just update the transaction without increasing the amount that they pay for it, then people can just spam the transaction pool, always resend the same nonce, and we have a lot of churn in the transaction pool, which is bad. Yeah, so here we add the we're trying to add the transaction to the transaction pool. We extract the sender, so we do the easy recover on the signature for the sender address, and we add it to the transaction pool, right? Ah, let's see. Sorry. Yeah, we add it to the transaction pool, and here we look if we already have the transaction in the transaction pool. We validate the transaction, and if it's underpriced, we discard it. And like there's a lot of stuff going on here, and in the end we enqueue the transaction. I wanted to go into detail about the transaction execution later on, but I can do that. No, I'm going to do it later on. So the basic idea is we're adding this transaction into the transaction pool, and somehow the transaction pool has like all of these transactions. Now we have to, if we go back to the picture, we started with our RPC, we submitted the transaction into the transaction pool. Now we have to send this transaction to our peers. So we have in the ETH protocol, in the ETH packet, so you can always see the packet that we're in up here if you don't know. And in the ETH packet we have the handler, and that handler has the sync transaction function, and whenever a new transaction, so it periodically asks the transaction pool for the pending transactions. So the pending we have because of someone we have different concepts in the transaction pool. Pending transactions are the transactions that are actually executable. We also have gapped transactions. So if I send a transaction that has nonce 9,000 and I didn't send 8,999 transactions before that, then this transaction is gapped. It's nonce gapped. Because there's some like weird there could be some race conditions about the transaction propagation. We actually don't want to throw away all of these gapped transactions, but we want to store a couple of them. So if someone then sends like the missing transactions, we can validate them and add them to the pending transactions. So what we do here is we get the pending transactions, and we send the hashes to a subset of our peers. So, oh yeah, it's some of the stuff is a bit hard to follow. But the idea is we shove the transactions into this announced channel, and now I have to. Oops, sorry. Here we go. I have to look where these transactions are actually ending up. Sorry. Here, yeah, in the broadcast. It's in ETH protocol ETH. Yeah, sometimes the package names and the packages are not really great. And yeah, so we shove in the handler, we shove the transaction into this queue, and we unqueue the transactions at the other end, and put them into this queue. And this is a infinite loop that runs. And if we have transactions in the queue, we get them. So we only have the transaction hashes in the queue. Yes. We actually fetch the transaction from the transaction pool if it's still there. If it by the time that we ended up here, the transaction is not anymore in the transaction pool, we just ignore it. But yeah, we add it to the pending, and we send the pooled transaction hashes. And here we go, back where we started. And this actually sends the transaction hashes to our peers. So what we do is we announce, like, there's two different ways that we send transactions. We either send so to a subset of our peers we send the full transactions, and to all peers we send the transaction hashes. And if someone receives a transaction hash that they're curious in, they can fetch it from our node. But we don't want, like, if we were to send our transactions to everyone, there would be extreme like transaction churn and a lot of bandwidth that we don't really need, because you would get all the transactions from every peer at all times, and so we don't want to do this. Yeah, so now we go to the P2P packet, and this just writes the message onto the wire. And yeah, so we managed to push the transaction to the peer. Now we have to go to the other side and actually receive the transaction. And this is done in the transaction fetcher. The transaction fetcher initiated here, and we have some loop, yes, and okay, I've never seen this code before. Yeah, so we, oh, that's a timeout, the wait, the notify. Yes, we get a notification of someone sending us transactions, and so we check whether we already got the transaction, we have the announcement from someone else. If not, we actually ask them to send the transaction. So we schedule the fetches, and for each peer we ask them for the transaction, and if they have the transaction, they send it to us, and if we get the transaction, we actually call the add transaction function. No, sorry, add transaction. This one. Okay, no, it's this. Sorry. Yeah, so this enqueues the transaction into the transaction pool. So this add transaction function is actually puts them back into the pool, and so we end up in the transaction pool again via add remotes. So we have we also have this concept in the transaction pool. We have the concept of remote transactions. Those are those that we get from our peers. And we have the concept of local transactions. Local transactions are those that we get over the RPC. We have to handle, we want to handle them differently because we don't want to drop our own transactions. So we always say, if you send a transaction over RPC, this transaction will never get dropped. If a transaction from the wire is replaced by something that pays more, then we can drop this transaction. And so we have this notion of local in the transaction pool. Sorry. And yeah, so that's roughly how transaction propagation works. And so the next interesting part is, how do we create a block? So the miner. Any questions to the transaction propagation? Yes.
The receiver peers. So how is it working? How is it gossiping the transaction further to other peers? So when I'm receiving a transaction, I'm recognizing I didn't saw this transaction yet, so I'm assuming then I'm just also doing the same thing. I'm forwarding to transaction to other peers.
You're forwarding to the square root of your peers. And then you're forwarding the hash to all the other peers. And if you receive a hash, then and you have never seen this transaction hash before, then you ask the peer that sent you this hash for the transaction.
Am I forwarding all of the transactions, or do I validate them first?
So I have to repeat the question. So the question was if we are forwarding all the transactions, or if we're validating them first and then forwarding. And the answer is we're validating all the transactions before forwarding. So our transaction pool only has valid-looking transactions. So valid-looking means the sender has enough money to cover the transaction cost, and the nonce is roughly what we expect. There might be some other conditions, but I don't know them. I'm quickly going to close the door because there's some sound coming from there. All right, let's get to creating a block. So now we have a lot of transactions in our transaction pool. We are a miner. We want to seal a block. How does this happen? For that, we have to go to the miner package, and the worker. Yes. So in the miner package, there's a lot of stuff going on. The miner is extremely complicated. So I already made sure that we're in the right vicinity. We somehow end up in the commit work function. So like the miner starts a loop, and whenever a new block comes in, we need to update our work package. so we need to build on top of the block that we just received. And for that, what we do is we prepare the work that generates sorry, no. All right, where were we? No, we were in the worker. Yes, commit work. We have to prepare the work. We have to F12. Yes, prepare work. All right. Yeah, we have to set a couple of fields in the block. For example, we have to set the parent hash to the correct hash. We have to set the correct timestamp. We have to calculate the gas limit. Per block, you can shift the gas limit by a tiny amount in either up or down. And so we have to we have some configuration, the gas ceiling or gas target. This is what we want what we want to end up with. So currently this is set by default set to 30 million. All the miners are trying to hit 30 million, but you can also configure this. And yeah, so we have to calculate the gas limit. We have to set the coin base. This is where all the transaction fees are ending up in the end. If we have London chain rules, then we need to do the base fee stuff. And we have so we have the consensus engine. This can be either ETHHash, Click, or the new Beacon consensus engine. And we have to make some environment. And so once we prepared the block, we actually need to fill it. So we need to apply the transactions. Sorry. So what we do is we fetch all the transactions, all the pending transactions from the transaction pool. Pending just takes the transactions that are actually executable. And then we first take the local transactions, order them, and then we take the remote transactions and order them. And then we commit the transaction to the pending block, to the pending work package that we're trying to build. And so what that does is, like, we have to set the gas limit and stuff like this. We calculate the sender again. We prepare the state, and so we have the state database, and we have to set some fields in there so that we can later on query them during the execution of the EVM. And then we call commit transaction, and commit transaction actually does apply transaction, and with apply transaction we go to the core package. So the core package is responsible for most of the core stuff. The TX pool lives there right now, which is not great. We should move that to its own package. Yeah, so all of the interesting like EVM stuff and is in the core package. So we're in the state processor now. We're creating a new EVM block context, a new EVM, and then we call apply transactions. Apply transaction does apply message, and apply message calls this new state transition.transaction database. And this is where we actually do the execution, or we start the execution of the EVM. So we start the execution of the EVM by doing the pre-check. The pre-check has stuff like get nonce. We verify the nonce. We verify that that's yeah, if it's not fake, yes. We verify that we actually have code there. No, we verify that the sender is an EOA. This is a pretty new change. Previously, it was theoretically possible to send a transaction from an address that had code deployed. It's not really feasible to do that because you have to find a collision between a code hash and an address that you know the private key for. But if you set code to an address that you know the private key for in the Genesis block, which is possible, then you could end up at some weird state. So we don't want to have transactions originating from a smart contract. Then we have to verify the base fee, and then we have to buy our gas. And buy gas just calculates how much gas we are, the maximum amount of gas that we are going to use in the EVM execution later on. All right, so we did the pre-checks. We have a lot of code here for tracing. So you can trace the transaction, you can trace each opcode, you can see which operations are executed, what's the outcome and stuff. So if you see config debug when something with tracer, you can just ignore it. It's not really interesting. And then we check the intrinsic gas. We check whether the sender has enough money. And if we are post Berlin, we prepare the access lists. So in the Berlin hard fork, we changed the rules a bit so that you can provide an optional access lists, and calls to this to the contracts that are in the access lists are cheaper. You can like pre-warm a contract, and we decided that calls to the precompiles, calls to the sender itself, and the recipient should also be warm cost. So the idea was we want to increase the cost for calling a cold address that we have to fetch from the state database, because that's a pretty expensive operation, and but that would break some contracts that have some like hard-coded limits for like interacting with another contract, and so these access lists are to unbreak those changes. And so in the future we can, they're optional right now. We could make them mandatory. Mandatory access lists is like the concept of mandatory access list is also something that comes up in stateless. If you're doing stateless, you will provide the pre-state as a kind of access list, execute the transaction, and then also provide the post-state so that everyone can verify without having to have the state. All right, and then we check if this is a contract creation. Contract creations are if you send a transaction to no address, to the zero address with code, then the code gets executed, and we call the create operation, and otherwise we call the code at the address that we sent to, that we're doing the execution to. Are you more interested in create or call? Create, call. Okay, let's do the call then. All right. In call, we're first checking if when you call a contract, you can attach value to that. So we're checking whether the node, the address that sent the transaction, the originator has enough money to cover that cost. Then we take a snapshot of the state database, and then we check the precompiles. And there was so there's some issue here. I don't know how many people actually know this, but back in the day, you could self-destruct contracts that, or like there was a hard fork after the Shanghai attacks that destructed all the addresses without code, without storage. And the problem was that Vitalik wrote a script to all of this, but unfortunately, and without a balance. Unfortunately, one of the precompiles also didn't have, like, it doesn't have code because it's a precompile. It also doesn't have storage, and it also didn't have a balance. And so he successfully destroyed the precompile. And so this clause actually checks that we don't hit that. All right, then we're doing the transfer. We're just sending the money. And if the code that we're sending the money to, or that we're calling, so we first send the money and then we're starting the code that is on there. If it's a precompile, we run the precompiled contract. So we in core VM we have the precompiles. Yes. Oh, in the contracts, yeah. Right. So this is like the different precompiles for the different rules. So, for example, in Istanbul, a new precompile was added, the Blake 2F precompile. So it's like that. There's different precompiles depending on the chain rules that we have. And these precompiles have a run function and a required gas function. So this, like, if you want to implement a precompile, you have to like fulfill this interface. And for example, the EC recover precompile for the required gas, it's a fixed amount. It's always 3,000, and if you run, it will validate the signature values, makes sure that we're not inputting something really weird, and then does the EC recover of the public key and returns the public key of that signature. And so this is like a pretty nice file. There's a lot of really cool things there, and I like this code a lot. Other than like some of the other code that I showed previously. And yeah, we're in the call again. If it's not a precompile, we get the code of the address that we just called. If there's no code, we're done. Well, not really done, but we're finished for now. If we have code at that address, we have to trigger that code, and so we set the call code. You have 3 different ways of triggering code. You have the call code, some other stuff, a static call. And then you call run on the contract, and run we fetch, basically we fetch in a for loop, we fetch the next operation, and then we look into the jump table to see the program that we have. Well, like program is like what the opcode actually does, and then we execute it. So how does an opcode look like in the EVM? You can see I don't know, we're going to for the London instruction set. Or we're going for the merge instruction set. You're probably all interested in the merge. Like okay, it doesn't do that much. Berlin, Istanbul. Okay, here we have some instruction sets where some instructions are actually set. So in Constantinople, we had a few new opcodes. We have the shift left, the shift right, the shift arithmetic right, xcode hash, create 2. And they all have a stack requirement, a gas function, and they have a constant gas and a dynamic gas if there's like some dynamic gas. So for some of the operations like add or sub, you like static gas makes sense. Like you're adding two 256-bit elements together. Like there's not much that can like grow out of bounds. But for some operations, you want dynamic gas, depending on the amount of work that you actually have to perform. And so, for example, for create, you want to have spend gas as much gas that's proportionally to the length of the code that you're going to deploy. And we can now look into one of these operations. So these are functions actually that are in there, and we can look at one of these functions. So, for example, the create function takes some stuff from the stack. It uses some gas, and then it calls the create2, which just creates an address and then calls create with that. And yeah, if we started with the create route, we would have ended up right here. But we wanted to look at call instead. So yeah, so that's roughly how the EVM works. You have these operations, maybe something easy. Op-add, yeah. So this is like an easier function in the EVM. You just take two values from the stack, add them together, and that's it. And yeah, so did the precompiles. Yes, and we are back in call. If something happens, so if there's some issue, if the contract reverts in the call, then we have to revert the transactions. And so, if you remember, we took a snapshot before we applied the transactions, and if it reverted, then we have to reload this snapshot and throw away all the modifications that we made to the state database. All right, and so after we executed the transaction, we know how much gas there was. We have some refunds. So, for example, if you clear storage, or if you call the self-destruct opcode, you're getting some gas refunded. And so we have to refund that. And we also have to pay the Coinbase. So this line is where the transaction fee actually goes to the Coinbase. And then we return the transaction result back to apply message and apply message. And now we have the result. And before Byzantium, we calculated an intermediate state root after every transaction. This is a lot of work, so after Byzantium, we decided to not do this anymore. And then we also have the receipt, where we set, if the transaction failed, we are going to set the failed in the receipt. You know, all understand this. And we also set the logs and the Plume. So the Plume is a Plume filter where all the logs are in. So the logs is every, like we have the return opcode that you can use to, wait, no, not the return. How do you emit an event? Well, whatever. Like if you emit an event in your smart contract, then it will end up in the logs. We want to filter these logs. So, for example, you are interested in all the events that originated from your contract that said, I don't know, send successful or whatever. So you have the send successful event. You have those are in the logs, and now you want to quickly filter through all the blocks, and this is where the Plume filter comes in. So we put all the logs into this Plume filter. What a Plume filter is, I know probably half of the room knows that. I don't know. I don't know if I should start going into this, but basically, you take some piece of data, you hash it, and you set some bits in this Plume filter, and later on you can hash it again and see if these bits are set, and if these bits are set, then you most probably had this event originate from. Or you did apply this event to the Plume filter beforehand. There's a chance that you didn't, and there's some hash collision. But it makes it very easy to query for logs, and to see if like something, if these events, if these logs actually are in the Plume filter. And sorry, it's 4,000 bytes, something like this. 2048 bit. Oh, it's fixed length. It's not really valuable anymore, and we would also like to get rid of it. But it was valuable at some point because you could just go through all the blocks, look at the Plume filter, and quickly decide, okay, this block has none of my stuff in it, so I'm just going to ignore it and look at the next block. If you actually find something in the Plume filter that looks like what you were looking for, then you need to go into the block, look at the receipts, and see if that was actually what you wanted. And yeah, that's basically it for apply message. And yeah, we just return the logs from the receipts. And we have some error conditions where we're back in the worker, where we committed the transaction to the pending, where we committed the transaction to the pending block. And now we have built a pending block. We took the first of all we set the fields like the parent hash and timestamp and stuff like that. Then we went through all the transactions, applied them one by one, and now we have a valid block. And now we need to actually finalize it, create the proof of work. But I'm unfortunately out of time. So we're going to do that some other time. Thank you very much.